Hello, good afternoon. Thank you very much for coming to our session. I'm David. I'm part of the team that has brought together the MI55 GPU, and particularly my responsibility is for the scale-up interconnect, which we're going to talk about today. And we're going to talk a little bit about how it's built and why we've built it using Ethernet technology. The first question I should answer, though, is why is it that we need to build a tremendously high-performance interconnect to connect together a group of 72 GPUs? And I'm not going to spend ages on this because you obviously have all seen Lisa Su's keynote, so you know the answer. But what it comes down to is the problems are getting bigger and bigger, and I'm not just talking about model size here. I'm also talking about things like the context size and all of that stuff. And what it comes down to is, in order to solve the big problems, you need multiple GPUs. And having a very high-performance interconnect to connect a large group of GPUs together allows you to solve these problems with higher performance and or higher efficiency. That's why we need a scale-up interconnect, and that's why it needs to be a large scale-up domain. A really key, important point is that these systems require very much a complete system view. So we're bringing together an awful lot of complex software, many components of hardware. In order to make it work well and efficiently, they all have to be designed together. So it's very much a systems view. And that applies absolutely to the bit that we're going to talk about, the scale-up network, which has been a close collaboration between AMD and Broadcom in order to co-design a great solution. So you've heard a little bit about Helios this morning. Some really big numbers on this slide, which I'm not going to talk you through and bore you to death. Obviously, what we're going to talk about is this enormous number here, which is, if you told me at the beginning of my career that's where we would be by now, I don't think anyone would have believed you. So the architecture of the scale-up interconnect, we'll come to in just a moment, sorry, but the important thing to understand is that we have multiple networks in these systems. The Helios rack consists of 18 nodes. Each node has a CPU and 4 GPUs. And we've got multiple networks interconnecting them all together. The first one is the front-side network, which is just your general-purpose data center network. It connects all of the nodes in a data center, and it provides you with the interface for management, orchestration, launching jobs, data ingest, all of that sort of stuff. The second network is the scale-out network. Now, this is a high-performance network connecting GPUs together in order to run workloads and allow you to build big jobs. This network typically spans all of the GPUs within a data center. It's typically InfiniBand or Ethernet. It runs RDMA protocols. It involves multiple layers of switching, all sorts of sophisticated features to manage congestion and give high performance. That's not what we're talking about today. Today we're talking about the scale-up interconnect. Now, the scale-up interconnect is a relatively new thing. It's a very high performance network, very tightly coupled, huge amounts of bandwidth, very low latency, and it allows multiple GPUs to work together very closely to give huge amounts of efficiency on these big jobs. The architecture of our scale-up interconnect, essentially it's built on a whole set of parallel Ethernet networks. So we have, in Helios, 12 Broadcom Tomahawk 6 switch ASICs. Each of those switch ASICs is connected to each of the GPUs with 3 400 gigabit Ethernet links. So in effect, what we have here is 36 parallel network planes. And every GPU is using every switch to talk to every other GPU. So when you're doing a data transfer, perhaps between this GPU here and one over here, you're spreading all of the data that you want to transfer across all of these links, so it's passing through all of the switches and then going down to the destination GPU. Now, this topology is excellent for a number of reasons. The first one is it allows us to scale bandwidth very effectively. So you get more bandwidth just by adding more switch ASICs. And of course, you can scale the other way. If you want less cost, you can omit some of your switch chips and get less bandwidth for less cost. The other key feature is that we only have a single layer of switching here. And that is absolutely brilliant for cost. It minimizes cost, it minimizes latency, it minimizes congestion. So it's absolutely the best topology. In terms of bandwidth, all of those switches are giving us 1.8 terabytes per second of bandwidth wherever we want to deploy it per GPU. So we can use all of that bandwidth just for this GPU to talk to one GPU, or because it's a switched interconnect, we can also use that bandwidth to communicate with lots of other GPUs. So we can deploy that bandwidth very flexibly. Now, the other features I'll talk about in just a moment. One of the key usability features is virtual pods. Now, virtual pods allow us to take this 18-node rack and split it into a number of virtual racks or virtual pods. A virtual pod is just a subset of the nodes, and the key features of virtual pods are, on the one hand, they provide you with performance isolation. So whatever's happening in one virtual pod will not affect the performance of other virtual pods. Secondly, it provides you with security. So it's impossible for the GPUs within one virtual pod to communicate with GPUs in other virtual pods. And the third thing it provides is resilience. So if you have a failure of some type within one virtual pod, that will be contained within that pod and it won't have any effect on the workloads running on other virtual pods. Now, failure resilience and fault resilience is a really, really important part of what we've done in Helios. We've spent an awful lot of energy on it. And Helios is really unique in its ability to tolerate and keep going in the face of failures. And in terms of the scale-up network, we can survive the failure of any individual link, any individual switch. We can also survive the failure of an entire switch tray. And the reason that we can do that is we've got all of these parallel network paths. And so if we lose a link or a switch, then we can redirect the traffic across the other parallel network planes and keep going. And all you do is lose the bandwidth associated with the failed links. And that's really, really, really key. Okay. The next thing I want to do is just talk through the technology stack top to bottom, just to make it clear exactly how this scale-up technology works. So obviously at the top, what we've got is a whole load of software. And AMD, of course, provides a complete stack of software, including device drivers, firmware, communication libraries, compilers. The communication libraries includes things like RICL, which implements communication collectives like all reduce and reduce scatter, which AI workloads are typically built on top of. And of course, AMD puts a lot of work into optimizing those and making sure that they are going to give the optimal performance on the Helios scale-up interconnect. But that's only a very small part of the software world. There's a huge ecosystem of third-party open source software, libraries, applications, and so on. Now, those communication libraries are built on top of the UALoE programming model. So UALoE is essentially UA link over Ethernet, and that's the technology name for the scale-up interconnect. And the programming model essentially is distributed shared memory. So the goal here is to allow each GPU to be able to read and write the memory of the other GPUs within the rack. So on the right-hand side there, we've got an application that wants to export, wants to export its memory so that it can be accessed by another GPU. So it's allocated a buffer in memory. It's got its own local mapping so that it can access that buffer. And it's going to invoke an export operation, which will return a registration key, and it passes that registration key across the front-side network to the other application. And the other application invokes an import operation. What that does is it creates a virtual memory mapping for that application onto the remote memory. So once you've got that mapping, the local processor on the GPU can do loads and stores, reads and writes through that virtual memory mapping and access the remote memory directly. The only difference compared to accessing local memory, of course, is bandwidth isn't quite as big, and the latency is a little bit higher. But otherwise, it behaves the same. As well as doing direct loads and stores from your programs, you can also use DMA to offload data movement. And in this example shown here, we're reading from local memory and writing across into remote memory. Now, underlying that load store semantic, of course, is the memory fabric built into the GPUs, known as Infinity Fabric. And what the UALoE technology does is it creates a bridge between the Infinity Fabrics in different GPUs. That bridge, of course, is built on top of Ethernet technology, which is where the Broadcom Tomahawk switches come in. And so the UALoE technology's job, on the one hand, is to take loads and stores and atomic transactions and somehow encode them onto Ethernet packets, transport them reliably across the network to the remote GPU, and then transport responses back in the other direction. We'll talk more about how that works in just a moment. Now, I want to highlight one aspect of the DMA because it's a huge improvement compared to previous generations. The key innovation in the DMA is that it has a split DMA architecture with front ends and back ends. So applications submit DMA data transfer requests to the front ends. Front ends will take those requests, split them into smaller chunks, and then distribute those chunks to multiple DMA backends. The backends are responsible for doing the actual data copies, so reading from local memory and writing across to remote memory. And a key point is that these DMA backends are distributed so that they're adjacent to the UALoE network adapters. And that means that the data transfer is very, very efficient. And it also means that with a single DMA request or a single DMA request queue, you can leverage all of the huge bandwidth of the scale-up interconnect. So it's very, very easy to get high performance with very little work from software. Now, I'm skipping a layer here. I'm going to go right to the bottom, which is the Ethernet layer. Why on earth did we choose to use Ethernet for our scale-up technology? Well, the answer is, on the one hand, there's a flippant answer, which is Ethernet always wins, which is something that people in the networking space have heard years over years, and it really has always been true. Once upon a time, it was going to be ATM that would destroy Ethernet, and then it was going to be InfiniBand that would destroy Ethernet, and Ethernet's still going. And it's still going because it continues to innovate. It keeps incorporating great features from other technologies when they are appropriate, and it has a huge amount of momentum and ecosystem behind it. Now, in our case, we chose Ethernet because there's a huge wealth of technology, of switches, of partners, of tools, telemetry, manageability, debuggability, all sorts of stuff that comes with Ethernet. And why would you invent something new when you've got such a great technology to build on? Ethernet itself is not enough to achieve a reliable, high-performance system. It gives you essentially a very high level of performance. It gives you a mostly in-order delivery semantic. It gives you a mostly reliable delivery, but not completely, because packets can get corrupted on the wire. They can get dropped. The switch, of course, could fail, and we want to survive all of those things. So we have to build a reliability layer on top of Ethernet in order to give us the properties that we want, which is a fully reliable interconnect. And that's the job of the UALoE technology. So onto each MI455 GPU, we have integrated just checking the time. Yeah, so we've got 18 of these UALoE NICs integrated onto each GPU. Each of them does 800 gigabits per second of bandwidth. Each of them essentially is doing the same job as a scale-out NIC. The difference is there's no way we can fit the area of 18 scale-out NICs onto a GPU. So it has to do that with a tiny, tiny footprint. So it has to be highly optimized and very, very efficient. And that means it's very, very specialized to the particular characteristics of the scale-up domain. The transport protocol itself is a lightweight, reliable transport protocol. Essentially, it behaves similarly to a TCP, but much simpler. It It has minimal overheads in order to give us the best possible bandwidth efficiency. And one of the ways that we achieve that is actually we use a custom encapsulation, including stealing some bytes from the Ethernet header. And that's part of the benefits of our collaboration with Broadcom, where we're using a special feature of their switches in order to achieve that. In order to get good efficiency, we want to pack multiple transactions into the same Ethernet packet. Now, a cost of doing that is that you get higher latency. So there's a dynamic packing algorithm that balances choosing short packets for low latency or large packets for efficiency, depending on the dynamics of the workload. And then finally, it leverages the Ethernet priority flow control feature to ensure that there are no packet drops when the network's congested. We've talked a bit about what we achieve with reliability and resilience in the earlier slides, but the way that that's actually implemented is if packets are lost, and particularly if we lose a link or a switch, what the UALoE transport does is it retransmits the lost packets across the alternative network path, and that's how it's able to then recover and continue. Finally, I just want to talk for 1 minute about security. Now, the goal here is to have a complete top-to-bottom secure solution for confidential computing, and that requires security at all layers. Firstly, the hardware, of course, is designed to be secure by design, with virtualization features, partitioning, memory encryption, all of those good things. Secure boot ensures, to get secure boot together with other features like device identity attestation and so on. These things ensure that the software can verify that the hardware it's running on is genuine and hasn't been tampered with, that the firmware is authorized, that the software stack is all secure. All of the I/O links that connect the different chips together, including the UALoE links, those are all using industry-grade encryption to protect the data in flight. And in particular, the UALoE technology is using packet-level encryption and integrity protection using AES 256. It's end-to-end security, so packets are encrypted as they leave the GPU and decrypted as they enter the GPU, and as a consequence, the switch is not part of the trusted computing base. I won't talk about the other features. And finally, we use TDISP to secure the interface between the software and the I/O devices. Now, together, all of these things provide a trusted execution environment that allows you to run confidential VMs in a fully secure environment. Okay, now that's everything I wanted to say. I'm going to hand over to Pete. Before I do, I wanted to say that this has been possible and is successful because of the close work that we've done together with our partners, Broadcom. And Pete, look forward to hearing all about Ethernet and Broadcom switches. Thank you.
Thanks, David. Thanks for an excellent overview of Helios and the scale-up architecture. My name is Pete Del Vecchio. I'm an AI infrastructure technologist at Broadcom, where I focus on networking and associated semiconductor technology for AI inference and training. I'd like to thank AMD for inviting Broadcom to present today, and also thank AMD, as David mentioned, for working with us very closely for a number of years to bring Helios to market. And for me, it's really satisfying to see, the highest performance AI system actually shipping in production right now with something we've collaborated on for a number of years. And of course, thanks to you all for attending today's presentation. My part of the talk will be on Ethernet for scale-up networking, in particular, why Ethernet was chosen, and specifically Tomahawk 6, for the Helios architecture. So before we get into the details, I wanted to make sure we're all sharing the same vocabulary. David went through some of this. Generally for AI networking, folks think of this as divided into 3 different domains: scale up, scale out, and scale across. As David mentioned, this scale up domain is a tightly coupled domain, effectively creating one compute unit. Those scale up domains, which are today fill a full rack, are connected together within a data center through scale out technology, usually with 1 or 2 layers of switching. And then for the largest GPU clusters, you actually need to put the GPUs in separate buildings. You simply just can't power all those GPUs in one data center. Those data centers can be in the same campus. They can also be in different regions. interconnect those data centers, you need to have this scale across technology. Key things we're focusing today is scale up. The key metrics are very low latency, high bandwidth, low power, and high reliability. I think another way to think of scale-up networking is effectively it enables memory sharing across GPUs. And in some ways, I like to think of this as a fourth domain of interconnect, where you have the scale up, scale out, scale across, and then there's this interconnect between the GPU and HBM, and the scale up is effectively an extension of that. So per MI450, huge amount of HBM bandwidth, so 23 terabytes per second. Per GPU is also 3.6 terabytes per second. So this really, I think, this high amount of bandwidth, the high ratio of HBM bandwidth to scale-up bandwidth, really speaks to the attention that AMD paid on data movement throughout the system. So again, you can consider scale-up to be memory sharing, and you think about, if you're doing memory transactions on this scale-up network, what features would you want in the network? So you'd want to have high bandwidth, high efficiency, so high efficiency as far as performance and also as far as power, and high reliability, because effectively, again, these are memory transactions that are going across the scale-up network. Okay, so why Ethernet for scale-up? First off, there are switches today. Ethernet has switches that will provide the low latency, the high bandwidth, the high packet rate that you need for scale-up networks. There are also features included such as, for reliable lossless operations, such as link layer retry, priority flow control, credit-based flow control. I'll get into some of these features in subsequent slides. Another very obvious or important reason is, Lisa Sue likes her props, I like my props too, is this. This is an Ethernet cable. You probably recognize this. These are ubiquitous. I mean, this technology, as David said, Ethernet always wins. I mean, part of it is because there is no other technology that has near the ecosystem, near the innovation of Ethernet. One important thing this allows you to do is, the last bullet here, is that it allows you to have the same technology stack across your AI infrastructure. This means that you can have a single pane of glass that actually looks at your front-end network, your scale-out network, your scale-up network, that shares the same telemetry, same management, the same tools. So what you see is that due to the benefits you have from, for Ethernet, the industry is really standardizing on Ethernet for the network layer and then continuing to innovate at the transport layer. And this gets into our next slide. So what does the architecture for Ethernet scale-up look like? So at the lowest layers here, you'll see that you standardize on Ethernet for the network layer. Most of you have probably heard of eSUN, or Ethernet for Scale-Up Networking. This was announced at OCP just last October, OCP Global. There's already a 1.0 spec out. It really speaks to the rapidity, how quickly we're bringing this to market, just the draw from the market to use Ethernet for scale-up. That 1.0 spec, it enables reliable lossless Ethernet, efficient support for small packages or packets, and then efficient multi-hop technologies. The founding members of eSUN are shown on the bottom here, which of course include AMD and Broadcom. So really we're seeing just across the industry that companies want to standardize on Ethernet as the networking layer, but again, they want to innovate at the transport layer. And what David went through in very good detail was UALoE. So this is, I think the GPU designers, they understand the data flows through the system, they understand their architectures, they understand the software better than anyone. So what you see is that throughout the industry, GPU designers want to be able to innovate, optimize their transport for their network, for their GPUs. UALoE is a great example of that. We also see that within OCP, there's SUE, or Scale-Up Ethernet. So that is an alternative transport. But you'll see a number of different transports now that are under development in the industry, all based on Ethernet as the networking layer. Okay, so just at high level again, I think you've seen this a couple times. So I won't go through all the numbers, but per Helios rack, 72 MI455s, there are 12 Tomahawk 6s, huge amount of bandwidth for scale up. In the end, This does allow you to have, one thing I think was important that David mentioned was this, that you have very resilient communication over 36 parallel networking planes. So very high degree of resiliency within this rack. Net result is that you have one large compute unit in the rack that has a distributed shared memory architecture and allows this rack to behave as a single tightly coupled computer. Okay, so why Tomahawk 6 in particular for Helios? Tomahawk 6 provides basically all the features that you would need for scale up. It has the high bandwidth, the high radix, very high packet rate, and that high packet rate is going to be important if you have a number of smaller memory transactions. It has a fully unified packet buffer. It's very low power. It provides the VLANs that are needed to create the vPods that David talked about, which in turn will provide between different jobs on shared hardware, security, and performance isolation. It also includes some features such as header compression that I'll get into in subsequent slides. It also has telemetry for the AFM or AMD Fabric Manager. Again, this is that single pane of glass throughout the network to analyze both the scale out, scale up, front-end network. As mentioned before, this is based on the open Ethernet. That's one thing you saw in the keynote today that Lisa really pushed was that this is an open platform based on open technology. And final reason I'll point out here is that there's been a very good, very close relationship between AMD and Broadcom in defining the specifications for this architecture, making sure our chips work together. Many of these features, things like header compression, link layer retry, they're becoming well known in the industry now, but we actually started developing this well before they were standardized. So that really speaks to the fact that we knew these features were important. We were able to collaborate closely together to bring these to market now. Let's see, in the interest of time, I'll go through this quickly here, okay, actually we got a little bit. Okay, so Tomahawk 6, I won't go through all the points here, but this is the world's first 102 terabit per second chip. And again, I like my props like Lisa does. So this is the Tomahawk 6 100 gig. This is, as far as I'm aware, the largest networking chip on the planet. It has 1,024 100 gig SerDes. And there's the reason I wore my cargo pants today. These are big chips. This is the Tomahawk 6 200 gig. So if you see, the packages are substantially different. The silicon on there looks very similar. So what we've done is to improve the efficiency to get the highest bandwidth for Helios, we use 200 gig SerDes. So you see the number of SerDes is actually half on the Tomahawk 6 200 gig versus the 100 gig. These chips are both shipping in production. They're very power efficient. They use 3 nanometer technology, have a number of features for having very high performance, such as our cognitive routing suite. We have fine-grained telemetry. And we also have options for both the 100 gig, 200 gig SerDes, and co-packaged optics. So physically, how is this deployed within the Helios rack? So what you'll see is that within the rack, there are 18 compute trays. So 9 towards the top, 9 towards the bottom. In between those are 6 switch trays. 4 MI450s per compute tray, 2 Tomahawk 6s per switch tray. An astounding number, almost 2,600, 2,600, 400 gig links in the rack, from the MI455s to the Tomahawk 6s. Tomahawk 6s actually provide about 3,100 links, so there's actually a little bit of spare bandwidth available from the Tomahawk 6s. So what's interesting here is that it's only 12 chips, 12 switch chips, 12 low-power switch chips, meaning that in the end, you actually spend a relatively low amount of power on networking, and every watt saved in the network means that you can deploy more AI compute. So getting into some of the features that Tomahawk 6 has that makes Helios efficient for having the whole system efficient on the scale-up network. One is compressed headers. So the scale-up domain, again, this is in one rack. You don't have the type of addressing, the type of features like MPLS and SRv6 that you would need in a broad data center network. If you look at a standard IPv4 packet, it's 46 bytes for the header. minimum size Ethernet packet is 64 bytes, so it doesn't give you very much room for the payload. Acknowledging the characteristics of a scale-up network, so much fewer nodes, this single hop network, means you can have a very, very optimized header. And that's what we've done here is we have flexibility in Tomahawk 6 to use optimized or compressed headers. So you wind up having small headers. In effect, that gives you, higher overall effective bandwidth. And this is especially important for small messages for smaller memory transactions. One other feature that's been leveraged for Helios is link layer retry. So what this does is that at the link layer, so between link partners, say between a switch and a GPU, you can actually detect errors at that link layer and then ask the sender to replay the packet. So unless the link is just about to fail, it's really poor, in almost every case, you'll actually successfully transmit the packet on that second attempt. So key feature here is that there's no loss detected above the link layer. It means that the IP, the transport, the application never see this error. It means handle it very quickly in hardware. So it enables this very efficient, lightweight transport that David had talked about. It means that on the silicon, it means the transport, the interface to the scale-up network can be very efficient. And when you've got 18 800 gig interfaces on a GPU, it's really important to make that transport as efficient as possible. Another feature that's leveraged from Tomahawk 6 is this very large unified packet buffer. So Tomahawk 6, so all the ports, all the priority queues, et cetera, all the packets go into one very large centralized buffer. What this allows you to do is it allows you to absorb bursts. I mean, we know that communication from GPU collectives, from AI collectives, are very bursty. So this large buffer can absorb those bursts. It also allows you to absorb incast traffic. So this is very common when you do things such as an all-reduce operation, where you have a number of GPUs sending to one destination, that you will get transient congestion to that destination. Large buffer also avoids head-of-line blocking, and then provides the performance isolation that, for shared hardware, especially when you have different vPods within one rack. So overall, this fully unified packet buffer will give you the highest efficiency, avoid congestion or absorb congestion in the network to give you the highest overall goodput. As mentioned before, AMD and Broadcom have collaborated very closely on this. This is a multi-year collaboration. We talked about some of these features: header compression, link layer retry. Telemetry is a big deal, both as far as network operations. So we enable an AFM edge agent for the switch. This is the AMD Fabric Manager. We enable fine-grained telemetry that is used for congestion control, for load balancing, et cetera. And then finally, joint validation. I mean, we jointly specified features. We did pre-silicon validation, post-silicon validation. And this was really critical, especially since many of these features are being standardized now, but were not standardized when we embarked upon this project. So I think, from my presentation, from David's presentation, you can see that, we're really advancing AI working together. We have, the best-in-class, industry-leading AI compute from AMD. We have the industry-leading AI networking from Broadcom. This is all based on Ethernet for scale-up networking. And in the end, we've provided you an open platform with the highest performance for your next-generation AI infrastructure. Okay, I'd like to thank you for attending, and we will now be open for questions if David would come up.
Awesome. Hold on just one moment.
So for scale out, we use UEC.
So UEC, the Ultra Ethernet Consortium,
Yeah.
So they're primarily focused on scale-out network technology.
Exactly.
So yes, absolutely. In Helios, we have the AMD Volcano AI NICs, which are the scale-out NICs, and those implement UEC transport for communication across, between racks and between GPUs.
Yeah, because the share of UEC from AMD.
So yeah, well, but the point is, UEC technology is not used directly as such in scale up. There is a relationship, though, which is that some of the features that are used in scale-up networks were first standardized in the UEC consortium, so LLR and CBFC, for example.
Yeah, I think that's a good point. I mean, we talked about eSUN. So when eSUN was formed in OCP, one of the goals was to get to market very quickly, and there's a huge demand for this. So the idea was like, not to recreate standards or create new standards where they're already available. So, they leverage, IEEE 802.3 for the PHY layer. As David mentioned, like LLR was already standardized within UEC. So eSUN is actually adopting some of the standards that are developed within UEC. Some of the other things, like the UEC 1.0 spec, that really was focused on scale out. So there's some things that we don't need to have here, but we've been able to pull in the features from UEC that are appropriate for a scale up network.
But also we have, beside eSUN, we have UALink. So we have UA.
Oh, UALink.
Yeah.
So UALink technology, obviously there's a relationship between that and UAL over Ethernet. Essentially, the primary difference is the choice of the switch technology, the fact that we've chosen Ethernet. And what that has come down to is that UALink did not exist when we started MI455. That technology has come along since then. So that's why we have an Ethernet-based solution, because Ethernet switches did exist. They had a roadmap. We knew that we would be able to get suitable Ethernet switches that would align with the timescales that we needed for MI455. That wasn't true of UALink.
Well, okay, so basically what happened was SUE, Scale-Up Ethernet, Broadcom contributed that to OCP. I think it was OCP Dublin last year. What we did there is we provided a full stack. I mean, there was a huge draw on the network for Ethernet for a scale-up network. So we provided full stack, networking all the way through transport. And what we've done actually is we've seen the need that people want to have Ethernet for that networking layer, and then innovated the transport layer. So that's where eSUN came out at the network layer. So now there's a SUE-T spec. So basically it's kind of bifurcated into two parts. We have eSUN, which is the networking layer. You have SUE-T or SUE transport, which is the other work stream that's now within OCP.
All right. And now we have another question as well.
Thank you for that. You obviously have a lot of optimizations for scale up, right? But we also use Broadcom switches for Rocky V2. So is it the same switch that we can use for both scale up and scale out with Rocky V2?
Yeah, so Tomahawk 6, basically we see a lot of deployments right now, both with scale up and with scale out. So yeah, it's the same silicon, just programmed differently and optimized differently.
Thanks.
All right, we have a few more questions and we have a limited amount of time left, so we're going to take probably two more.
Okay. With NVLink 5, there is a limit of 575 GPUs, the scale up. With UALink, it's 1,024. Is there a similar limit with your technology here?
Well,
in terms of the size of the GPUs?
The potential maximum size of the number of GPUs in a single scale-up domain, is that what you mean? Yeah.
Across multiple
so,
racks.
Yeah, there are different places where you can potentially have limits on scale, and it depends on what trade-offs you're willing to make. So within our GPUs, of course, the hardware design itself has limits on address width, I should say, that place one limit.
Yeah.
Ethernet itself doesn't constrain us in any way. The addressing space in Ethernet is enormous.
Yeah.
Even if we use technologies like UFH, which is a new compressed header format that has 16-bit addresses, even that would allow us to get to 64K GPUs in a scale-up domain. So that there's not really a limit at the network layer. The main limit, from my point of view, is that there are practical limits. So on the one hand, you really would strongly prefer to have a single layer of switching for the reasons that I talked about earlier. Yeah. Okay, it's much, much more cost-effective and better performance. And switches have a finite radix. So the number of ports on one switch is a really important limit. But actually, another really important limit is how many GPUs can you get close enough to the switch to actually connect them? So there are physical difficulties with concentrating that much power and achieving long enough cables between the switches and the GPUs that just make it very difficult to go to really large numbers of GPUs within a scale-up domain. And I think those are the limits that actually in practice limit us.
Okay, thank you.
All right, we have time for one more. We'll go to the side of the room.
Hi. So Lisa this morning talked a little bit about disaggregated inference with Cerebras. I'm wondering if you could comment a little bit about how disaggregated inference will impact the scale-up network.
Yeah, so it's an interesting question actually, because I'm not, so despite working for AMD, this collaboration with Cerebras is news to me as well. So what I don't have a good picture of is exactly how the Helios MI455s will be talking to their GPUs, their wafers. So it's very difficult for me to say anything intelligent there. I mean, clearly, given that the goal is very low latency, very high interactivity, we're going to want to have a very fast communication path between the two. But I can't answer your question, sorry. Okay, I think, is that time up, Jesse?
Yes, that is.
Great. Well, thank you very much indeed for attending. Really appreciate your time.